Hello, everyone. Thank you for joining us this afternoon for the 10th Charles Rolls and Henry Royce Memorial Lecture. My name is Bill Crossley. I'm the J. William Uhrig and Anastasia Vornas Head of Aeronautics and Astronautics here at Purdue. And it's my pleasure to welcome you to this event. With the reopening of campus this fall and our adherence with the Protect Purdue guidance, I'm really happy that we're actually able to have people here in person today. This is the first time we've done something like this since the pandemic started. So thanks for joining us today. Let me tell you a little bit about the Charles Royce and Henry Royce Memorial Lecture Series. It started in 2002. Typically, it's been a biannual event. Obviously, we got off the even years for obvious reasons, so we're picking that back up again with the 10th event this year. This lecture series is presented by Rolls-Royce and by the School of Aeronautics and Astronautics here at Purdue. The series brings leaders in aviation and aerospace to campus with several aims in mind. This lecture series inspires our students to pursue careers in aviation and aerospace by allowing them to hear from the distinguished speakers. The lecture series highlights Rolls-Royce's heritage and connection to the aerospace industry as a major provider of power and propulsion for civil and defense aviation. And the lecture series celebrates the strong and continuing collaboration between Rolls-Royce and Purdue. This partnership between Rolls-Royce and Purdue has existed for several decades. And just in August of this year, you probably heard about the most recent major development in this relationship. Rolls-Royce launched a major investment project in partnership with Purdue and the Purdue Research Foundation to develop new facilities here for high altitude and hybrid electric engine testing to power the next generation of US military aircraft. We've had we've had many collaborations, let me put it that way. Let me highlight a few other ones just to give you some context for the relationship between Rolls and Purdue. In 2003, Rolls-Royce established its first United States-based University Technology Center here at Purdue. It's focused on high Mach propulsion. That's evolved to focus now on advanced thermal management systems. In 2016, not too long ago, Rolls-Royce designated Purdue as a university technology partner, which really recognized the number of contributions we make across advanced aircraft engine technologies, turbine and compressor aerodynamics, materials research, control systems, and some recent initiatives in cybersecurity and digital technologies. In 2017, many of you probably noticed the opening of what everybody calls the Rolls-Royce building, even though it's not its official name. Rolls-Royce was our first corporate partner in what we call basically the aerospace district here at Purdue. Again, showing a huge step that they've made in the relationship with us here at Purdue. The most recent data I have say there's about 600 Purdue employees in Indianapolis and West Lafayette working for Rolls-Royce. That's another really strong connection. A lot of Rolls-Royce employees are our alums, and they serve on advisory committees, and they come up and support a number of different events here for students at Purdue. So in the spirit of celebrating the strong partnership between Rolls-Royce and Purdue, I'm really happy to introduce to you our guest and speaker for the 2021 Charles Rolls and Henry Royce Memorial Lecture, Dr. Marla PerezDavis. Dr. Perez-Davis is the director of the National Aeronautics and Space Administration's John H. Glenn Research Center, just outside of Cleveland, Ohio. As the NASA Glenn Research Center director, she provides the planning, organization, and direction needed for the more than 3,200 employees there. And their job is to accomplish missions that in turn support NASA's missions in aeronautics and space exploration. NASA Glenn really touches aeronautics and space in their endeavors. Prior to becoming the center director, Dr. Perez-Davis served in many roles of increasing visibility and responsibility at NASA Glenn. Just to give you some of her background and show what an illustrious career she's had, she served as chief of the electrochemistry branch, leading efforts in energy storage and power management, probably building on her PhD in chemical engineering. She moved to the position of chief of the project liaison and integration office, where she showed important organizational skills to improve their business processes, contract management, and safety assurance activities. She came back to the technical world a little bit more as director of the Aeronautics Research Office, where NASA Glenn's work supported NASA's Aeronautics Mission Directorate and their Aeronautics Research Mission. She then served as deputy director for research and engineering at Glenn, and then immediately prior to her current role as center director, she served as Glenn's deputy director. As she moved through these roles, Dr. Perez-Davis' efforts and accomplishments have been recognized through numerous NASA awards, including the NASA Outstanding Leadership Medal and the Presidential Rank Award for Meritorious Executives. People outside of NASA noticed Dr. Perez's accomplishments, and here's a few that she lists in her bio, and I just wanted to give you a sense of all the different organizations that have recognized Marla in her career. She's been listed in the top 25 elite businesswomen by Hispanic Business Magazine. She was in the 2015 Cranes Women of Note. She received the Women of Color Career Achievement Award. She received the Distinguished Alumni Award from the Alumni Association of the University of Puerto Rico, Moyagas. She received the Women in Aerospace Award for Aerospace Awareness. She received the Women of Color Technology Award for Career Achievement and the Hispanic Engineer National Achievement Santiago Rodriguez Diversity Award. Dr. Perez-Davis is a native of Puerto Rico. She earned a bachelor's degree from the University of Puerto Rico, a master's degree from the University of Toledo, and a PhD from Case Western Reserve in chemical engineering. So as I mentioned earlier, I'm really pleased to have someone like Dr. Perez-Davis here to share with you and me some insights and innovation about innovation in flight and aeronautics and astronauts. So with that, would you please join me in welcoming Marla PerezDavis to the podium?
Thank you, Bill. All right, let's fix things here. Back to my size. Good afternoon. All right, you gotta wake up. All right, that's good. All right, couple of things first. It's the first time I have this type of mask, so I'm practicing at the same time that I talk, so my apologies, because again, it's take a little bit of adjustment. Let's see, couple of things about my lecture this afternoon. It is a little bit of educational. It's a little bit of what we do at NASA Glenn. But I think that one thing that I encourage all of you is to, as you listen to me talking or you're watching the videos, some of the videos that we have, think about your role and how you can be inspired and motivated to really join us in the journey of present and future. So that's your homework. I know some of you are taking notes. Just write a note, because now the professor on me took over. Write a note about how do you see yourself in this role, and what do you think you can do to help us in our mission. So with that, I'm going to start. As I said, it's going to be a little bit of everything. And I have my notes because I want to make sure that I touch in all the points throughout my presentation. So good afternoon again, and thank you for inviting me to speak today at this year's Charles Royce and Henry Royce Memorial Lecture. I would first like to thank Bill for that warm introduction. Thank you, Bill. And I would like to acknowledge the other distinguished guests in the audience. And I would be remiss if I didn't thank the entire team here at the School of Aeronautics and Astronautics for inviting me and for the amazing and informative tour this morning. It has been a busy day, but it has been just outstanding. If any of you are some of the students that were involved in this morning, I saw some of you by the posters, thank you so much. It goes without saying that it's not the same thing to read about some of these things that see your level of enthusiasm, your knowledge, and your commitment to the research that you're conducting. So on behalf of NASA, and I'm sure you can say Rolls-Royce and the Purdue University, thank you. There are many great things happening here at Purdue, and I stand here today inspired by the research and the progress taking place, and I live here knowing Purdue will continue to lead us into the future of flight and space travel. In preparing this lecture, I began to reflect upon my career in aerospace, my center, and the 43 Purdue alumni currently working at NASA Glenn and living in Ohio. I began to wonder what a couple of brothers from Dayton would think about the world that we live today. Can I have this slide number 2? It is hard to believe that almost 118 years ago, humans took their first powered flight. And that short flight set us on a course to do some incredible things in a time frame that is nearly incomprehensible given the technology available in 1903. From the dunes of Kitty Hawk, flight quickly progressed, and by 1927, Charles Lindbergh was flying non-stop across the Atlantic in the spirit of St. Louis. And he was followed just a few years later by Amelia Earhart. Just 20 years after Lindbergh's flight, Chuck Yeager broke the sound barrier, ripping across the skies of California in the Bell X-1. Going from supersonic flight to orbiting the Earth took only 15 years when John Glenn, whom my center is named after, made his laps around the Earth. 7 years later, a guy from a small town of Ohio made the next giant leap aerospace achievement, stepping foot on the moon for the very first time. We continue to advance aviation and spaceflight with the emergence of reusable spacecraft, optimization of the tube and wing aircraft, and by putting the International Space Station into orbit, which has remained crewed and operational for nearly 21 consecutive years. Today, we live in a world where we have conducted multiple power flights on Mars. We have commercial companies regularly delivering supplies and astronauts to orbit, and we are preparing to usher in the next era of supersonic commercial flight and ready to send astronauts back to the moon so we can go to Mars in the coming decades. A tremendous amount of innovation and change has occurred over the past century. And all of it is because a couple of guys got a wild idea that they could fly, and they were followed by pioneers who refused to let the sky be the limit. What does the next century have in store for humanity? Next one. So we're going from Purdue to the moon. One of those pioneers is an individual who was educated here at Purdue. Neil Armstrong enrolled right around the time Chuck Yeager was breaking the sound barrier. He spent 2 years studying engineering before being called to active duty as a naval aviator during the Korean War. When he returned, Armstrong joined the National Advisory Committee for Aeronautics in 1955. His son, Mark, recently told me was his lowest paying option, but getting into the agency was his goal, not the pay. While many people know of NASA's accolade, what many don't know is that his first assignment with the agency was in Cleveland, Ohio, at Lewis Research Center, now Glenn Research Center. Because of his role and because he's son of Ohio, we recently renamed one of our major campuses after Armstrong, given the test facility play a critical role in the safety of spaceflight and the next era of electric aviation, which we'll discuss later. After leaving Cleveland, he went to the high-speed flight facility in California, which is known as NASA Armstrong Flight Research Center. Over the next 17 years, he served as an engineer, test pilot, and later on as an astronaut. Number 4.
This is the new ocean, and we must sail upon it, and we must be a leader on it. And that caught people's imagination.
Many people look at NASA and think only of a space flight, but we started as an aeronautics agency, and we continue to play a critical role in the development and testing of many aircraft systems. We like to say, NASA is with you when you fly, because every aircraft flying today has NASA-developed technology on it. But how does NASA benefit the nation, and why is aviation important to the US economy? NASA's work in aeronautics directly benefits in an aviation sector that annually generates more than $1.5 trillion in US economic activity, and an aerospace positive trade balance of nearly $78 billion. The impact of aviation is incredible, and another impressive way to look at how aviation impacts our economy is the number of passengers flown in 2019 is enough to fill every NFL stadium in the United States 440 times. The weight of cargo carried in 2019 is about the same as the weight of 3,672 Great Walls of China, which is considered the heaviest man-made object on Earth, coming in around 116 billion pounds. These are pre-COVID numbers, and the total impact of the pandemic on the aviation industry is yet to be determined. But NASA is leaning into these challenges. We are helping industry and government partners to regain public confidence in our aviation system while accelerating research and development to identify new opportunities for rapid adoption of new technologies to help us adjust to the new environment. Number 6. So let's talk about the flight technologies we are working on, and more specifically at NASA Glenn. Number 7. NASA is investing in technologies aimed at changing the aviation industry as we know it. These developments vary from basic materials to full-scale experimental aircraft, all designed to increase efficiency and reliability, while decreasing weight and cost. NASA Glenn engineers are developing innovative new materials that can be used to manufacture better parts for aircraft and related systems. One of these materials is silicon carbide fiber-reinforced ceramic matrix composite. This lightweight and reusable fiber material is ideal for high-performance machinery, like aircraft engines, because they are capable of withstanding operating temperatures up to 2,700 degrees Fahrenheit and are strong enough to last months or even years between maintenance cycles. Our team developed a state-of-the-art process for reinforcement of silicon carbide fibers that improve performance and durability. It also provides expanded design flexibility for specific applications and shapes without any loss in durability. We're also using shape memory alloys, one of my favorite technologies, to replace hydraulic actuators that operate flight controls and control surfaces, which will significantly reduce weight and improve part reliability. We have conducted laboratory tests by folding an F-18 wing with shape memory alloys that you see in the video on screen, as the one in the lower corner, which will eliminate significant weight from the aircraft wings, allowing for more fuel or payload. We also use shape memory alloys actuators through our span-wise adaptive wing project, where the actuators were installed on a small-scale drone to demonstrate the material's ability to fold the outer wing sections and their control surfaces to optimal angles during flight. We're also teamed with Boeing to install deployable smart vortex generator made of shape memory alloys on its Echo demonstrator aircraft for in-flight testing. These smart vortex generators will reduce drag throughout the entire in the flight, improving overall performance, which translates into direct benefit for passengers. By introducing more advanced materials like the shape memory alloys, we can gradually replace hydraulic and pneumatic power with electric power, aiding the reduction of mass, fuel consumption, emission, and cost for future aircraft. Another material is magnetic materials, and NASA investigates the feasibility of hybrid and all-electric aircraft. Several key electric power-related components and materials need to be developed or redefined to meet the ambitious power goals. These future electrical aircraft require high power, greater than 1 megawatt propulsion systems that are lightweight, fault-tolerant, and reliable. However, engineers are currently limited to off-the-shelf components that were not optimized for use in aeronautics. These components are too heavy for many practical aviation uses and exhibit excessively high losses at the desired conversion frequencies, which creates significant power loss and large amount of waste heat. Our Materials and Structure division is working to increase the efficiency and specific power of a wide range of energy generation and conversion components for aircraft and other applications. And this work begins with the advancements of soft magnetic materials. By developing these low-loss soft magnetic materials and components, we are, by way, designing smaller, more lightweight power conversion components for aircraft, power electronics that can run at a much higher frequencies required for electric aircraft. We are demonstrating this by developing nanocomposite soft magnetic materials. One of the advantages of these alloys is that they're capable of operating at high power densities, frequencies, and temperatures that conventional materials while maintaining lower losses. Next one. And as a Glenn, we also like to say, we freeze to please. Give the center our role in the international research on aircraft and engine icing. Most ice protection technologies in use today were largely developed by NASA Glenn, and we continue to provide tools and information to inform industry and regulatory agencies on the range of icing conditions to increase aircraft safety. And we are now looking into new technologies, like ice-phobic materials, flight software, and computational modeling to better understand ice accretion on advanced airframe for future aircraft configurations to assess the icing risk during the development phase. Regarding engine icing, ice crystals found at high altitude near convective clouds can enter a propulsion system core, leading to ice buildup and potentially catastrophic situations, such as uncommanded rollback, engine stall, surge, and damage due to ice shedding. Our engine icing technical plan highlights the 3 research areas of emphasis: flight characterization of the high ice water content environment, research around altitude testing for engine components, and fundamental studies of ice particle aerothermodynamics, and computational research to simulate engine performance, ice accretion, and engine control methods. We see exponential growth in this research area with the wide application for both airframes and in the engines across UAS, on-demand, and large aircraft. A key area of emphasis at Glenn is increasing knowledge and detailed understanding of highly integrated propulsion and aircraft systems. We are putting emphasis on boundary layer injection propulsion systems with configurations that capitalize on ingesting and energizing the boundary layer to reduce drag and increasing efficiency. It is accepted that the boundary layer injection could deliver improved aircraft performance, including significant reduction in fuel burn. We're talking about 5 to 7% of that fuel burn reduction. Drag and weight without sacrificing fan efficiency due to the highly distorted airflow. We test the first ever boundary layer injection distortion tolerant fan at high speed to prove the system level benefit of the unique distortion tolerant inlet fan combination. There is a continuous interest in this work from multiple airframe and engine manufacturers, military and academy. This testing has opened the door to a new type of jet engine, and we are excited about the results and potential steps forward. In the area of acoustic, we think about, the noise at airplanes now, so let's talk about noise now. The cities need vibrant airports to enable local businesses to thrive, to join the global marketplace, and to draw to the world to their doorstep. Noise is a big factor in the viability of airport. And NASA is working technologies for quieter aircraft, which enhances the health and quality of lives of residents living near airports while enabling the benefits of aviation for everyone. Propulsion noise is a dominant source of the existing aircraft fleet and a potential barrier to emerging aviation markets, such as the advanced air mobility and high-speed commercial flights. At Glenn, we mature technologies and design tools to create quieter, cleaner, and more efficient propulsion system, supporting a sustainable, environmental compatible future for global aviation. To enable future even quieter engines, we have recently renovated our 9-foot by 15-foot low-speed wind tunnel, making it top tier for propulsor acoustic testing, and we also research in our unique aeroacoustic propulsion lab for quieter nozzles and engine installation. One thing I would like to say is that as we invest in developing the technologies, we also have the challenges of matching our capabilities to be able to test in those facilities. And the best example is this tunnel. It has served us for many, many years. What happened is the technologies got so good that now we have to modify the tunnel to be able to really measure the noise generated by the technology. So it is a good thing. It's just that we need to continue investing because the capabilities, now we surpass the ability to measure on those capabilities. At Glenn, we're bringing also our experience in advanced communications to the emerging market of advanced air mobility. To ensure safe and seamless integration, Glenn has been working with industry, the FAA, and other agencies to enable beyond visual line of sight operations, as this is a critical hurdle to overcome in accomplishing our future flight goals. These efforts include working to establish secure data links, identifying technical and environmental challenges like weather and terrain, and we're working to improve and maintain safe aircraft control from the ground. We are bringing together the community of innovators, vehicle builders, and service providers to educate and challenge them about what is really required to safely operate in an urban environment. It is not just about the vehicle. It is about the infrastructure and systems needed to support operations. While our work in this area is extremely important for today's world, I am especially excited about the research and development we are doing at NASA to usher in the future of flight. Slide number 9. The tube and wing design is working well for all of us. But while there have been vast improvement in materials, engines, and avionics, today's commercial aircraft structure remain more or less the same as those in 1960s. Our past 50 years, we have optimized to their full potential. There really isn't much more we can do with the tube and wing. So we need to shift the paradigm. We need to think radically, need to embrace the unknowns of what is possible for the commercial aviation industry. NASA's vision of future flight looks very different from today's world. We will make the world smaller, while on-demand flight services that will move people across our country and the globe in ways we could only imagine a few years ago. We will have cargo-laden drones and air taxis as a part of a daily life servicing rural communities that don't have easy access to flights, and in high-density urban areas, shorting daily commuters. We will cut travel times in half or better, flying on supersonic and perhaps hypersonic, commercial aircraft, and highly efficient subsonic aircraft, all residing within the same ultra-safe airspace. There are many opportunities to meet the challenges of our globally connected world, an opportunity to establish a new S-curve. But to make it happen, we need to make proper investment in our future, in our students, and in the transportation economy founded on sustainable energy. The innovative aeronautics research investment made today by the government and across industry and academia will be realized tomorrow in technological and economic benefits, well-paying jobs, and significant life improvement for the traveling public and our planet. Slide number 10. Advanced air mobility has the potential to change our daily lives for the better, much like the invention of the wheel, railroad, combustion engine, and aircraft. And NASA plays a critical role in working with partners from across the country on AAM and the national campaign. NASA defines AAM as a new and efficient method for safely moving people and cargo in underserved areas and in challenging urban environments. At Glenn, we are working to help NASA usher in the future by studying how electric systems can be optimized. We are looking at supporting technology development to improve engine and power components on the order of magnitude required, as well as vital work on around propulsion acoustics to help limit noise. We are working to establish secure data links and real-time communications to safely integrate these systems into the national airspace. Number 12. Today, there is significant demand for high-performance, fuel-efficient, low operational cost aircraft that coincide with an ultimatum for cleaner and quieter air travel. This global demand is driving the growth of the research and development into a more electric aircraft market, to both increase the aircraft performance and reduce cost, but to meet the focus of the public, regulatory bodies, and manufacturers regarding adoption of environmental friendly technologies. However, the initial cost of developing more electric propulsion systems and the technical challenges of size, weight, and reliability of electrical systems are significant barriers to bringing an electric commercial aircraft to market. These technical challenges are within our grasp, but we cannot do it without the collaboration with industry. The thermal management is critical to making these more electric aircraft viable. This begins with the integration of power and thermal components from the start, and we cannot continue to build to try to add components after turbines have already been built. We cannot allow the addition of electrical components to negatively impact aircraft performance. So this will force us to look at designing turbines different, which is good. The second challenge is investing more in high power density or small core turbines. By doing this, it will enable advancement in conventional turbines, including higher bypass and hybrid electric. And smaller cores will help offset all the additional weight added by generation, converters, thermal management, and other components. NASA Aeronautics is working on these challenges to keep US companies economically competitive as they innovate to bring to market the next generation of environmental sustainable commercial aircraft, ensuring continued US leadership in aviation. We have a lot of work to do, but we are already well down that path. Next one. We see electrified propulsion as one of the key drivers of changing the way we travel. The advancement of electric propulsion system is one of the core competencies of NASA Glenn, and is the key for future aircraft to be cleaner, more efficient, and more cost-effective. This is also an area that has more recently generated the interest of engineers, companies, and academia across the globe, from both traditional aviation and urban air mobility perspective. NASA has been working to address these challenges the way the power extraction and storage and thermal management, created by introducing more electric components into larger aircraft powertrains, and we will need industry and academia to help us succeed. For large regional aircraft and sustainable flight is on the development. We are developing hybrid electric and turboelectric propulsion, including enabling green technologies like advanced magnetic material power electronics and energy storage and thermal management system. We are already well down the path to increasing the power density of powertrain components, and we are now ready to start pursuing flight testing of a megawatt class system with our electric powertrain flight demonstrator project, which will start testing in the coming years. We're also aggressively pursuing next-generation small-core aircraft engines with aims to develop advanced gas turbines to reduce fuel burn by 5 and 10% through increasing thermal efficiency. We're also operating a world-class reconfigurable facility dedicated to the advancement of electric propulsion technologies for small and large commercial aircraft, what we call the NASA Electric Aircraft Test Bed, or NEAT, and is located at the Neil A. Armstrong Test Facility in Sandusky, Ohio. There is where we conducted the first megawatt-scale aircraft powertrain test, taking advantage of the facility's 24 megawatts of available power. NEAT also includes a vacuum chamber, which can currently simulate altitudes up to 40,000 feet to test high-voltage power electric motors and controls. This is a one-of-a-kind that makes NASA Glenn a destination for aircraft electrical powertrain development, and NASA and our many commercial partners will continue to carry out research and testing there to years to come. Next. Next one. It has been almost 20 years since commercial supersonic flight has been available to travelers. When the Concorde succumbed to financial difficulties, excessive maintenance and fuel costs, and ticket prices that were perhaps a little too high for average travelers. However, the case for high-speed commercial airlines traveling between Mach 2 and 4 that can cut travel times in half or better has never been stronger. There are a number of start-up companies like Boom Supersonic who are currently developing and testing prototype supersonic aircraft. They are doing so with the goal of producing smaller 50 to 75 passenger aircraft for over-the-ocean supersonic flight, and their concepts are so promising and financially reasonable that United Airlines has agreed to purchase up to 50 of their aircraft to begin flights by 2021. This entry point makes sense, using smaller, more efficient aircraft that will allow airlines and airframers to figure out what routes are most popular while also meeting what will be assumed to be high prices and small demand, at least initially. Only after gaining an understanding of passenger demands and route map can we work together for large passenger and cargo aircraft, bringing the many benefits to the masses. Key to this future and the financial viability of high-speed commercial flight is overland flight, especially given most of the world's daily flights happen over the Centennial United States. But to make that a reality, we must first figure out how to quiet the sonic boom. Next one. NASA and industry partners have already matured design tools, technologies, and aircraft shapes to alter how supersonic shock waves behave. So instead of the shock waves coming together to create a loud boom boom, the shock waves do not merge and rapidly weaken it, resulting in a sound more like a soft thump and or what we believe will be as loud as a car door closing. NASA and Lockheed Martin Skunk Works are developing a pilot low-boom X-plane, known as the X59 Quest, which is designed to validate the unique boom-reducing features, but it is important to note that this is an experimental plane and not a prototype for future airlines. Part of what makes the aircraft unique is its shape and its top-mounted engine, which features a unique inlet to provide smooth, uninterrupted airflow at both transonic and supersonic speed. As of now, the X59 is completing assembly at Lockheed Martin, and its first flight is scheduled for mid-next year with acoustic validation and Armstrong Flight Research Center before it embarks on community overflights in the United States starting in 2024. Data collected during those community overflights will share with US and international regulators to help them set new rules that could allow supersonic flight over land. Let's take a look at some of the testing NASA Glenn has done on the scale model of the X59 in our 8-foot by 6-foot supersonic wind tunnel. Next. Also under this high-speed flight effort, NASA Glenn is developing critical technologies and advancing core test capabilities to enable reusable hypersonic systems. This research focuses on solving some of the most difficult challenges in hypersonic flight, and the collective NASA Hypersonic Technology project team is performing fundamental research and developing technologies, including propulsion system analysis, turbine-based combined cycle, mode transitions, sensors for adaptive control and health monitoring, and high-temperature durable materials for propulsion and control surfaces. The NASA Hypersonic Technology project is working with several DoD and industry partners to support of high-priority ground and flight tests, including the use of NASA Glenn Propulsion System Lab, the 10x10, and the 8x6-foot supersonic wind tunnels, to conduct this high-speed research needed for the nation. Another capability at NASA Glenn is our hypersonic test facility at the Armstrong Test Facility. It was originally designed to test nuclear thermal rocket nozzles. This is a hypersonic, blow-down, non-vitiated, free jet facility to test large-scale hypersonic and air-breathing propulsion system. Next. All right, now we're going to talk about the future of STEM. So I know I told you it was going to be a little bit educational, that it was going to be a lot of information about what we do at NASA Glenn. Now let's talk about you. What is the role that you play in all of that? So I gave all of you homework at the beginning, so I hope that some of you get yourself into either the subsonic, because you're already engaged. I have the opportunity to listen to some of you this morning. Supersonic, which is really a big challenge of going from subsonic. We have a lot of knowledge, but you jump into another flight regime, the challenges magnified in some areas. You are the future of the nation. You are the future of what we do today and what we will do tomorrow. And when I say what we will do today, because it's your responsibility in terms of what you are learning here at Purdue, what you learn in collaboration with industry. Obviously, Royce is a big player in what we're doing within, the aeronautics development of technologies. And thank you for the time that you spent with us yesterday. And the collaboration throughout the years, because that's, one thing that I talk about. We don't do things by ourselves. We do that in collaboration with industry and with academia. So back to all of you and your homework. As I said, we need you. We need your creativity, we need your innovation, but we need your brain power. If we look at the number of alumni that we have at Glenn, we do have a great number. We're very proud of every single employee that works at NASA and NASA Glenn. We're very proud of the group of alumni that came out of Purdue. You are that next generation. So the question is, what are you doing? I hope that all of you get motivated to look for an internship activities to support aeronautics, but also to support the space side of the house. There's big challenges. Some of you probably are working on these areas right now. And some of you probably in this audience are working with us as some of our pathway interns and or trying to get into one of the positions that we have open right now at NASA Glenn. So it's important that you take responsibility for your career, to take responsibility for your development. And the first thing that I will say is, activities like today where you get to know who is working in what kind of technologies, who is working in areas that you're passionate and that you bring value, knowledge to the table. Make sure that you take the time to look into those opportunities with industry, with academia, with federal agencies, because the future of aviation is with you. I can talk here for hours. I can tell you all the great things that we're working on, but that's only one step. The next step is yours. Only you, and only you, can take responsibility for that. There's a lot of exciting things here. Just imagine this. Imagine that you are that young engineer, scientist, researcher, business person, legal person, it really doesn't matter what your role, that really come out solving the challenge, one of the biggest challenges that really propel the ability of us to fly supersonic and hypersonic. Imagine that you are that person that come out with that thermal system that makes sure that we can fly hybrid electric or electric systems. Imagine that you are that person that come out with the component that makes sure that we can send our astronaut to be sustainable on the moon and live on the moon. Imagine you are that person that come out with the design that really take advantage of the electric propulsion systems, nuclear systems, the propulsion system that we need to go to Mars and being able to bring our astronauts safe to planet Earth. Imagine you are the person that designed the shape and the form of the plane that we need to take advantage of hypersonic for commercial aircraft. Just imagine. Dream big, like we say at NASA. Dream big. Because to meet some of these demands, we all have to dream big. And we all have to do our part. So that's your challenge. That's your homework from now to the end of time. Because you also have the right to change direction and adapt. And you will have to do that not just one, but multiple times in your life and in your career. And that's okay. But dream big. Challenge yourself. Because we do need you. We need that brain power. And thank you for being here. So next one. Gonna have the next, okay. University Leadership Initiative is one of the things that we're doing at NASA to get universities involved and academia involved with our activities. We have one here in Purdue, and I really ask you to take advantage of the information and really try to find more. One of the things that we do with any of these initiatives is we also learn. We learn from you, we learn from the universities, we learn from the commercial partners that universities have, and we improve on that. It's not static, it changes with time. And when we said we all have our responsibility, that is part of our responsibility. I am challenging you to find your path, but we also have the responsibility to help you find that path. So we are working very hard to come out with ways to get you involved in our activities early on to make sure that we take advantage of your innovation, creativity, and the way of you to look and solve problems. So this is one of the initiatives that we have going currently to make sure that we do our part, educating the next generation of scientists, engineers, and researchers. And I think I'm coming to my last chart, which is my closing statement. So when we look ahead over the next 20 or 30 years, we see much exciting work needs to be done. Those challenges laying ahead are going to break the status quo and truly embrace the next generation aircraft. And be assured that NASA is making significant strides in all of these areas we have outlined today as we work toward the future of aviation. As I said before, we are not in the business of building engines and electrical systems. Our role is to identify challenges, investigate solutions, bring everyone together, and push companies, students, and individuals to place you maybe we have not gone before, with the industry and academia to collaborate to ensure we are maturing the right concepts, implementing new technologies, and preparing for future flight demonstration. This is an exciting time, and we believe we are at the right place at the right time with the right technology. In closing, again, I want you all to embrace the change and the spirit that has influenced aviation innovators for more than a century. Our success is based in collaboration, and it must be multidisciplinary in nature if we are going to succeed. all of you here in this room at this very moment are more than capable of making what may currently seem impossible a reality. And I look forward to what you will accomplish in the future. Thank you.
Thank you, Marla, so much for the great talk. It reminds me of why I became an aerospace engineer. I mean, urban air mobility, advanced air mobility, we're working in that here. Supersonics, we're talking about that here. Hybrid electric aircraft, sustainable aviation. What an outstanding talk. Thank you so much.
My pleasure.
Marla's going to be willing to take some questions. We have a few microphones set up on stands. I think what we'd like to do is, if you have a question, please walk up and get in line and we'll alternate. So I'll give you a second or two to think about a question. Nobody ever wants to go first. I should have planted one of my graduate students to go first. And all my graduate students are sinking in their chairs.
No, we can always, we have plenty to select from. We can just
start
ask.
picking. We can start,
they
they don't like that when I do that in class either. Does someone have a question would like to ask Dr. Perez-Davis?
Any questions? Yeah.
Yeah, if you wouldn't mind, we are recording, so that way the people on the recording can hear the question too.
Hi. So in regards to the advanced mobility of aircrafts, you had some pictures up there of aircrafts that may be landing and taking off from buildings. And how do you feel about the laws in America, you know, how we're really restrictive, especially after 9/11 and all that? Do you feel like those laws are going to change significantly where you can allow aircrafts to take off from wherever?
So that's one of the things that we're working on, the technologies to enable the regulators to set the standards for where to take off and where to land. The other thing is the communication technologies that are needed for the safe space. So we are not in the business of developing the drones, or we're in the business of developing the technology and getting the information that is needed for regulators to do what you just said. How we can take advantage of the technology but be safe. How we can enable security and ultra-safe airspace. Because we still, if we are the drones, and we all know that it's being used for commercial application, it is a technology that can really reduce the cost and really open the boundaries for the market and the commercial entities. At the same time, we have to make sure that we have ways to secure the space, the airspace. So the communication technologies, ground to ground, air to air, how we can make sure we have all these devices and there's a way to monitor and control the use of the devices. Again, it's a technology that can open the economic markets, so we want to do that. We just have to find how to do it in a safe way. And obviously, you still have some other devices, right? We still have planes, different type of aircraft, so we have to add that component to the equation. Thank you for the question.
My question is kind of regarding these sustainable aircrafts that you were talking about. Were those intended to be, are you working on like fully electric aircraft or just electric supported aircraft? Because I read somewhere that like it's not possible mathematically to have a fully electric aircraft just because of like Newton's laws and stuff like that.
So there's different, like everything, right? There's different conditions, requirement that we have to define. Are we talking about 1 or 2 passengers? If you go into the 1 or 2 passengers, there's already all electric aircraft there. So the question is how we can, have the technologies to enable either hybrid electric. If you look at hybrid electric, right, how we can use more electric components. The use of electric motors, rely less on the fuel, more into the electric component. And then how we can move from the hybrid electric to all electric. Now that's what I said, we have to think different because we probably cannot take a plane the way we look today and just change a couple of parts and say it's all electric. The weight, the cost. We go from dealing with electrical systems, right? Once you get electrical system, you also have to add the thermal management, which I mentioned a couple of times, because now you have to have another challenge, how to release that thermal heat that is get there. So again, it's just the challenges, but one thing that I will ask you to think about, and some of you are too young to know this, so for the audience that is, a little more my age, when people start talking about electric cars, many of us thought there's no way we're gonna have electric car. There's no way I'm gonna drive an electric car. Why? Because I have no desire to go only 100 miles and then have to charge my car, right? I don't have any desire to go 40 miles per hour on the interstate. There's no way I'm doing that. Look at the electric cars these days. So I would challenge you to think that maybe it's not tomorrow, because we're working very hard in all of these technologies, but NASA is going to have a technology demonstrator. And again, the technology demonstrator is not the way it's going to look, but it's the first step to close the gap on those technologies. So think about the progress that we have made on the electric cars. That's the same way it's probably going to be in aviation. It's going to take time, it's going to take innovation, and it's going to take some technologies that we do not have right now. And that's what I said, that's where you play the role. Because sometimes we look at the same problem and we try to find the same solutions, because we are conditioned to think only one way. When you look at the problem, you don't have any bias at that point in time. So your idea may be like, let's do it this, and we probably will say, well, I'm not so sure that's a good idea, but we're probably gonna try it, and guess what? That may be the solution. So again, think about what we have made progress, and yes, there's challenges. It's not an easy task, and that's why we work on things, because they're not easy, because they're hard.
Thank you.
Hi, so I attended a seminar about the future of electric aircraft at the EAA Air Show this year. And I was kind of surprised to find out that a lot of private pilots in the community were really aggressively uncomfortable with the idea of electric aircraft because of what it would mean for current existing aircrafts and warbirds and incompatibility with fuel. So I was wondering if there's any initiatives to kind of connect with the smaller flying industry, not just large commercial operations?
So I think, we work in all the regimes. Again, I would be careful because we develop the technologies for the planes, right? We look at the technology from the standpoint, but your point is well taken. There's the piece about the aircraft, how we change, how we design, how we solve some of these technological challenges. And then there's the infrastructure to support that kind of architect. So yes, your point is well taken. I'm sure there's others working that kind of challenges in terms of what is the infrastructure that we need and the changes from a fuel to a more electric. This is just my opinion, but I think, like anything else, the way that we fly today is the way we fly today. We're making also improvements and changes in terms of small core, the turbines, the air breathing propulsion. That is still part of the way we fly today, is going to stay with us. The question is, what is the future? So it's the past, the present, and the future. So it will maybe two, it may be three different ways that we fly. Is the question of all of these missions have a benefit, how we can capture the benefit and how we can help also in terms of green technologies. And obviously electrical power is one way to be into the sustainable and in more green technologies.
So you're talking about how applying electric propulsion to aircrafts and such, and that possibly being a near-term future. What is the possibility of expanding it to spacecrafts and satellites and using that as a new way of propulsion instead of current way?
So there's different type of propulsion. If we took a space, right, we talk electric propulsion is very different from electric propulsion for a space application. Solar electric propulsion is one of the technologies that we are developing in NASA Glenn for deep space exploration. The first element of the gateway is based on solid electric propulsion, the power and propulsion elements. There's very difference into one another in terms of the kind of trust and how you generate that trust too. So we're talking two different things, but there's a convergence in between aeronautics and space, and that is in terms of the fundamental knowledge that you need to be enable some of these technologies. Thermal management. Obviously, we talk about, for example, cryogenic thermal management. That cryogenic is very different from space than aeronautics, but the fundamental aspects are very similar. The question is how the knowledge that you gain in one can be transferred to the other. For example, in the area of batteries, lithium ion is the battery that we use, right? But lithium ion, we started using that more in space, and then we matching that for the needs in aircraft. Obviously, it cannot do all the things that we need to the electrical aircraft. That's what we talk more about hybrid. That's what we talk about electric motors. So I think, it's the question of what is the knowledge that we gain in one that you can transfer to the other. But there's different propulsion systems. Solar electric propulsion is very different. It's using, the solar arrays pretty much to get the propulsion that you need to be able to move, the satellites or combination of the thruster and, the solar arrays. So there's different combination. And again, that's the other piece, right? Depending on the requirements, depending on the mission, is what are the technologies that you're gonna look at. But there's always something that you learn out of that, especially when there are big challenges, because there's a good chance that you can transfer that knowledge from aeronautics to space or from space to aeronautics.
Let me come up and thank Marla here real quick. So, one more question. I'm sorry, I didn't see it. I'm sorry. Please go right ahead.
Yeah, so kind of a more general question. I think it's no secret that aeronautics has been considered impossible by a lot of people for a long time, and that we're especially NASA, no stranger to taking on impossible problems. But how do you go about both keeping yourself open to the things that are considered impossible but are really just improbable, while still ruling out the things that we all know are directly against, like, I don't know, perpetual motion and stuff like that?
Yeah, that's a big challenge, and it takes some balance. It also depends on the priorities in terms of the agency. So right now, for example, we're still working the air breathing propulsion, but we're also investing in the electric propulsion. We always try to continue adding value to the exploration of space, value to the aeronautic community. And it takes a balance between past, what you learn, what you invested today, and what you have to do in the future. When you're developing technologies, you have to start today for something that you need 5, 10, 15 years tomorrow. I mentioned solar electric propulsion. We will not have solar electric propulsion if we will not have been starting the investment 20 years. We will not have electrified propulsion. We will not be looking at these components if we will not have started that idea about 15 years ago when we said, will that be possible? And again, we did the math and said, there's no way. There's no way that we can lift a plane. There's no way we can take off with electric systems. But we said, we have a seed, we plan the idea of the impossible. And that's what we get to the possible. It takes time. It takes an investment, it takes a commitment, and again, it takes resources. And the resources are the people and the capabilities that we have as a nation. Our ability to really sustain the economy is directly related to our ability to sustain a viable technology base here. And NASA, we do that for space and aeronautics in collaboration with industry and academia. Excellent question.
Thank you.
Great, thank you. And thanks everyone for coming this afternoon. I really appreciate it. It's as an instructor and a teacher here at Purdue, it's neat to see people here again after the last year, which is really quite awkward. So I have a small bag of trinkets, and they are trinkets because I know there's rules about what we can give the government employees. I think the total here, you might be able to exchange for a latte at the Leafs if you did that. So we made sure we stayed there, but there are a few Purdue souvenirs for you to thank you for being our 2021 Charles Rolls and Henry Royce Memorial speakers. So thank you, Dr. Perez-Davis. Now, to wrap up this event this evening, I'd like to invite John Kusnerick. He's the Vice President for Military Strategic Systems at Rolls-Royce to come up and provide a few closing comments for us. John, please come on up. And again, my thanks to Rolls-Royce for co-sponsoring this lecture series with us.
Oh, it's an absolute pleasure. So more specifically, I actually lead Liberty Works, which is about a few miles down the road in Indianapolis. That's our innovation hub. We work on everything from basic research all the way to applied technology, rapid prototyping, all sorts of things that Dr. Perez-Davis just described to us. Things that, to reflect upon, the Wright brothers would have thought were impossible when they were working with technology. But we work with that every day. It's an absolute delight to have Dr. Perez-Davis join us and brief us on behalf of Rolls-Royce. We want to absolutely thank you for what you've provided us today. I think it was inspiring, very thought-provoking. If you think about it, step back, hypersonic flight on a regular basis, supersonic airliners writ large, urban air mobility, a way to move people and packages very differently than what you would see today, emissions-free aircraft, electric propulsion, and it's just simply incredible. The future is bright. I would congratulate the students here on selecting Purdue. It's a great school. Welcome. You're already a part of aerospace. Welcome to aerospace. On behalf of Rolls-Royce, we would ask you to imagine big and do what you love. With that, there is a reception with some cookies after this, and boiler up.
So again, one last time, my thanks for participating today. Normally we'd have a reception where we'd all mill around with each other inside the building and be eating food, which is something we don't really want to do right now. So what we've decided to do is we've got a cookies to go reception. So there are some cookies and bottled water off here to my left, which will be your right. Usually I get that mixed up, but I actually did it right for a change. To your right. And then we've allowed some space out between the Union and Stewart Center, which is right next to us. There's a kind of a patio area. And we'll all walk out there, and Dr. Perez-Davis will join us, and we'll have a chance to interact with each other and with her. So again, my thanks for attending this afternoon. Thank you very much. Have a good afternoon.